So, vielen herzlichen Dank für diesen sehr lehrreichen Vortrag. Er steht schon, macht sich schon bereit, Professor Dr. Nicola Scafetta von der Neapel-Universität aus Italien. Er wird uns heute über die Grenzen der Klimawissenschaft was erzählen zum Thema Sonnenvariabilität, natürliche Zyklen und Modellunsicherheiten. Ich begrüße auf der Bühne Professor Dr. Nicola Scafetta. Vielen Dank.
Okay, so my talk today is the frontier of climate science, solar variability, natural cycle, and the model uncertainty. So actually, this talk is mostly about this book that I have written. Okay, I have written. So if you would like to give a look to the book, then we can do that later, okay? And so what is the main characteristics of this book? Of course, the book is a scientific book. As you see here, it's based on more than 650 peer-review papers. And of course, there are my own research, but there are also the research of many, many people. This is because climate science is a very complex topic. So do not believe that everything is settled. So the book is called Frontiers of Climate Science because many things are still open, many issues are still open, and practically in any field of climate science, there are open issues, and scientists are addressing these complex issues. So it is not true that climate science is settled. Perhaps somebody of you may know that last summer, the Department of Energy of the United States of America has published this report, a critical review of impacts of greenhouse gas emission on the US climate. So what I am going to tell you is that essentially there are many scientists who are actually questioning this global warming alarmism, and because of science, okay, not just because of some ideology or of some politics. And because, as I told you, this science is not settled. So let us briefly tell you what are the main issues here. Now, global warming. This is the global warming during the last, since 1850. You see that the temperature went up by a little bit more than 1 degree, 1.1, 1.2 degree. The big scientific issue is whether this warming that has been recorded is due to natural factors or to anthropogenic factors, okay, so nature and humans. Now, what it is told to us is what the IPCC concludes. And this picture here tells you exactly what how the IPCC interprets climate change during this period. And these are essentially the data, the results. And you see here that practically the global warming has been due to anthropogenic factors, which are here. There are several components of anthropogenic factors. But the important thing is this result that is here. Okay, so these are the solar component and the internal variability component. So this can be considered the natural component of climate change. And it is very clear what is the results of the IPCC. Solar and natural variability had contributed 0 to the global warming observed during the last 170 years, okay? So this is what the IPCC concludes. The issue is that, and this is how the IPCC essentially try to prove that the results. So by using climate models, what they do is to run the climate models in two ways. On one side, they run the models using all forcings, natural and anthropogenic, and they get these simulations, these brown simulations, and then they run the same models by using only natural forcing, so solar and volcanic forcing, and they get this kind of simulation, this blue simulation that you see here. And it is clear that if you believe in these models, that without anthropogenic forcing, climate would have remained nearly constant during these 170 years. Now, these results may appear very strong, but indeed, here there is a huge problem in physics, okay? So, because according to the scientific method, a prediction, a model prediction, must be tested against the observations, okay? So you need to test the prediction against real data to be sure that your model actually describes reality. And what you see in this picture is that in the case of the brown simulations, that prediction is compared against the data, which are this black line that is here. But in the case of the most important prediction, so the prediction regarding the effect of natural variability, solar natural variability, as you see here, you do not see any data. There is no comparison with observed data. And this because the reason is that, of course, there is no planet B, there is no a twin Earth equal to our Earth without human emissions, from where we can get the climatic data and compare that data against the prediction of the model. But if we do not have this testing, if we cannot do this testing, we can say that the models are not validated, okay? Are not validated from a scientific point of view, because you don't have the proof that this interpretation is correct, okay? So that is very simple concept. You don't have the data to prove that the models, this interpretation and more. So what is the anthropogenic global warming theory? It's a theory based on computer modeling. If you believe in the models, if you believe that the models are correct, then that is fine. Humans are 100% responsible of the global warming. But in physics, it's not based on a belief, okay? You cannot say, I believe in the models. I need to prove that the models describe reality, and the prediction of the model, the main prediction of the model, which is this one, cannot be tested. That is very simple. Therefore, we need to investigate whether there are evidences that may confirm this interpretation, or there are evidences that question this interpretation, okay? So let us do a little bit of, let us start from the beginning. So essentially how the models are used. The models are used by doing these simulations, that they are used to do some prediction based on scenarios, different scenarios of emissions, as you see here. Then these emissions, these simulations are compared against some kind of risk assessments in several fields. What you see here is that essentially you have some vulnerability, climate vulnerability if the global temperature will rise above 2 Celsius degrees since the pre-industrial period, which is the period between 1850 and 1900. So you guys start to get some problem here, and here, essentially. And then what you see here? You see here, so what is the scenario that allowed us to remain below the 2 Celsius degree? You see here that the scenarios here is the SSP1, okay? The SSP1 are the net zero politics, no? So that will get this SSP1 scenario. So all other situations, SSP2, SSP3, and so on, will cross this 2 Celsius degree threshold. And so people say, well, if we would like to prevent some risk, we need to realize the net zero politics, okay? So this is the logic that has been done. But of course, all this depends on the models, whether or not these models are trustful or not. And we have seen before that we do not have evidence that these models are actually correct. But that is what people are doing, so it's all based on this net zero attempt. So we need to reach this net zero to save the world, and nobody is actually doing that because net zero policies are extremely expensive, so people do not really can do that, okay? So it will destroy most of the economy of the rich countries. So you have all these tension between the bureaucrats in Europe that would like to realize this net zero and people that are realizing more and more that economically is not safe. And there is another problem here, as you see in this picture. Europe, this is the amount of CO2 in the world, okay? So you see that European country actually they do not count much in CO2 emissions. So the big amount of CO2 production is actually in Asia, as you see here, China and India. So you do not really get much there. So practically Europe is going down, the emission in Europe is going down because of this politics, but in the rest of the world you see that the things are going up and up, so there is not much to hope that Europe could save the world, so because the rest of the world is not doing much in any case, okay? So, and you see here why. So in Asia there is a huge amount of coal factories that are being built right now, and so there is no way that this can change soon. So we need decades to change. So there are some issues here, very important issues that we need to address. Now, first of all, which shared socioeconomic pathway is realistic? So we have seen that the models, the prediction depends on these scenarios, socioeconomic scenarios for the future. The issue is which one may be realistic. And so that here there is something very interesting. So what people have realized during the last 5 years is that some of the scenarios that the IPCC was using, like for example the SSP5 and also the SSP3, may be very likely unrealistic because most countries are actually following what here is the SSP2 scenarios. And why this is important? This is important because almost all climate alarmism is based on simulations that are used the SSP5 emissions scenarios. Okay, so, but if this is not realistic, also that risk assessments is not realistic, so it doesn't make any sense anymore. And now people have actually realized that that kind of simulations are not realistic. You see here some risk assessment from the IPCC, which are actually based on the SSP5, and so if this is not realistic, you can just trash all this stuff because, of course, it's just a game, okay? Now, so what we have here are the climate models. The climate models, according to several scenarios, the SSP1, 2, 3, and 5. So these simulations, we can say these simulations are retired now, are being retired, so we should not care too much about this simulation. What we are doing is something like this. The SSP2. This is instead SSP1 is the net zero scenario, okay? And, okay, so, but still we have open issue here. Still we have open issue. So, the first one, the second important issue is that which models could be realistic. And why this? Why this? Because there is a big issue regarding, for example, the sensitivity of the climate sensitivity to the radiative forcing. So we have CO2, which is a forcing, but we have also feedbacks, okay? We have also feedbacks from the forcing, which is a problem here. And essentially here, the issue is here, essentially, if we double CO2, if we increase CO2 in the atmosphere, from the theory, from the greenhouse theory, so the warming will be relatively moderate, okay? So if we double CO2, the warming will be about 1 degree Celsius, okay, from doubling CO2. But the climate models have the feedback. So there is the need to calculate the response of the climate system to a change of the forcing. And what is the problem here is that the climate feedbacks, there is a huge uncertainty regarding the climate feedback. Now, this huge uncertainty regarding the climate feedback actually is a not solved problem, because here you have the uncertainty in the climate sensitivity since 1979 to today, and you see here that essentially people were not able to reduce this uncertainty. And if you are not able to reduce this uncertainty, that means that you have not solved the climate, the main climate issue, okay? That is to calculate the sensitivity of the climate system to some radiative forcing, okay? And so, again, the science cannot be considered settled because the uncertainty has remained more or less the same for more than 50 years. Although during the last years there were a number of papers, Lewis, Scafetta, and the other people who essentially claimed that the real climate sensitivity may be low, In any case, what the climate models do is this is shown in this picture. So we have many climate models made by many people around the world, and these numbers are the climate sensitivity predicted by these models. Again, we have models that predict a very low climate sensitivity, so for doubling the same amount of CO2, and models like this one that predict a very high climate sensitivity, 5.6. So from 1.8 to 5.6, there is a factor of 3. So you understand this is a huge uncertainty. This is again, so why there is this huge uncertainty? Because these models cannot really be tested, validated against the data, because as I showed at the beginning, you do not have an Earth without humans against which to test the models. Okay, so you have this huge uncertainty. So again, the science cannot be considered settled. But what happened during the last years? Okay, there were a lot of papers came out, and they are talking about this hot model problem. Many models show two warming. So there is some problem there. Essentially, this is an example of this. This is from one of my papers. You see here that if we divide the models in three groups, the high sensitivity models, the low sensitivity models, and the middle sensitivity models, so the models are these yellow curves here, the black one are the data. You see that only the low sensitivity models may be catching the data, okay? Can be maybe catching the warming observed since 1980. So you see that these models here, most of these models are too warm. These are the dots are each model. Most of the models are too warm relative to the observations. But there is a bigger issue here because you see that there is this line here. This line corresponds to the warming since 1980, measured by the satellites. And the satellites are measuring less warming than what you get from the surface record. And if the satellites measurements are the real one, okay, are the correct one, then you have that practically all models are running too hot, okay, are running too hot. So practically that means that you cannot use any of them. There are other issues regarding, this is a picture from the IPCC that compares the warming predicted by the models in the troposphere, so not just on the surface, but for all the troposphere. It compares the prediction of the models that are these red curves here against the data that are these black curves. And you see here that the models predict a much greater warming than what the data are actually observing. So this means that since 1980, essentially the models do not get the correct warming of the atmosphere. So by putting all together this information, very likely, that is my impression, is that in the literature, the equilibrium of climate sensitivity, there is a huge error in the climate sensitivity. The models used now have this range, okay, so between 1.5 and 6. The IPCC claims the range of the climate sensitivity is this one, but very likely, by considering that most models are actually getting too warm, you have this, that the climate sensitivity is very likely low. So you cannot really use many models. So most models, you cannot use them because the climate sensitivity is very likely below 3 Celsius degree and very likely between 1 and 2 actually, so we will see. Now there is a third issue, that critical issue of climate model. Okay, we have talked about climate models, but are these models correct? Are these models physically correct? Okay, so do they have all physics, or there is something missing there? And and then there is another issue. So the climate data that we are using, do they have some warm bias? Okay, so because we need also to test whether or not these records, these climate records, may be realistic. Okay, that because we need to test whether the data are correct. This is because the data that we are using to estimate climate change, indeed, they are not real data, because those are data products of statistical models. Okay, so we take the data from weather stations or other things, and then the data are put together in some way by using some homogenization algorithm, and so it's a very complex statistical model. Okay, so what you get is not a real temperature of the Earth. There is not a thermometer that is measuring the temperature of the Earth. Okay, so what we get is the output of a statistical model that try to put together all data, meteorological data, and so on, from the land, from the sea, and so on, that we have. And we need to test this data because there is some issue here. So these issues are shown here in this picture. So you see here a difference between the red curve and the blue curve. The blue curve are the data of the world that are estimated by the satellites. The red one instead are the data from the surface record. And you see that the satellites are measuring less warming than the surface record. So this is just one issue. Then in this other issue here, we are comparing data from the rural station alone and the total data. The red one are the total data, the blue one are the data from the rural station, because there was this issue of the urban heat island, the effect of the urban heat island that could be still present inside the surface record. And you see here that there is a difference, a clear difference between the two records. The urban station seems to have less warming than what the global data show. But this is a very interesting curve here, because here we are comparing the land and the sea curves, okay? And we are comparing the surface record with the satellite record. So the red one are the land record. These are the satellite records above the lands, and you see that there is a huge difference between what the satellites are measuring and what the land records are getting. So you get much less warming from the satellites over the land. But if we go over the ocean, you get that there is the satellite records more or less coincide with what you get from the sea records, okay, from the sea surface records. So you get something very, very close. So this suggests that something strange is happening on the land, okay, because the satellites probably are working well both on the sea and over the land, but there is something on the land records that is biasing the record. Now this one is very interesting also, because the blue one, what is this? Is the record obtained with the trees, okay? So it's a temperature record obtained with the trees. So we are inside the forest, so are proxy records, but we have this reconstruction with the trees, and they get this blue line over the same regions. The temperature record from the surface gives this red line. So you see that there is a huge difference again, okay? So practically the trees are not getting the warm that the temperature in the weather stations are getting. Okay, this means that there is something like a urban heat island effects that is said to be corrected by the homogenization algorithms. It's still there, okay? It is still there. It's blending around instead of being corrected. So trees don't have that warming, essentially. And there is another issue here regarding the fact that the homogenization algorithm have been changed in time, and practically you see here that there is several surface record So these are the head CRU record from England, and different version. There are 3, 4, or 5, and you see that if you move from the 3 to the 5, you get more and more warming. So something strange happened here, so you get more and more warming just because you change the algorithm that with whom you are talking in data. But remains this big issue. No? So from the land we have the surface is getting some warming, but in the rural area, the warming is less. You have also this large warming during the 40s, 1940s. Then there was a cooling, then warming that is well recorded, in particular in the rural station. And what you see here is a kind of estimate to check where there might be some bias on the surface. The red dots here is where the bias is more likely. This is based on an algorithm that compares the maximum temperature and the minimum temperature, so because most of the warming due to the cities, for example, will occur during night. Okay, so if the warming, the night warming went up too much, that is an indication of a local warming, okay? It's a warming on like a urban heat warming, something like that. And you see here these red spots around here. Many of these red spots actually may suggest that there is some huge problem on the lands, that the meteorological stations are getting the local weather, okay? So they will affected by many things around. So my conclusion, first conclusion is that very likely the climate records that are being used are biased. There is a warm bias against this in this record. Perhaps 20% of these records of the warming shown by these records is fake, okay? So it's just urban heat island that has remained inside the global record. They were not able to clean up this bias, okay? Okay, so this is one point. So the first point was that the climate models very likely have a too high climate sensitivity to radiative forcing, so we need to use at the most low climate sensitivity models. The second issue is that very likely the global warming, the real global warming is a little bit less than what reported, okay, because 20% less probably. The third big issue is that there is a natural climate variability. Although the climate models claim that natural climate variability had zero effect on the warming during the last 170 years, natural climate variability is a reality. Okay, so everybody studying the history of the climate of the Earth knows that the climate has always changed. Okay. And it has changed in some way that actually appears to be, these changes appears to be characterized by several oscillations, okay? So these are not real random variations, but they appear to be characterized by some kind of oscillations. And these oscillations some of them are very long, so we are talking about 150 million oscillations, which are this one, okay, this one, and then oscillations that are the Milankovitch oscillations, which are linked to variation of the orbit of the Earth. Then we have a set of millennial oscillations, millennial secular oscillations, which are very likely due to solar variability. okay, and other things that we talk about. And then we have shorter oscillations like El Niño oscillations, quasi-biennial oscillation, and then, of course, we have the annual cycle. So the climate of the Earth is always changed, and the records are showing a lot of oscillations. Most of these oscillations are very likely of astronomical origin. So this means that if you would like to really understand the climate change, you need to look at the sky and go beyond the sky, because this is something that has to do with the orbit of the Earth, with the sun, with the planets, with the stars, galaxy, and so on. So it's something very, very huge. You cannot just look at the Earth. You need to look also at the space if you would like to understand climate change. And so now let us look at what the models perform, how the models perform if we look at the past. Because we have seen at the beginning that the models predicted that natural climate variability practically does not give any warming during the last 170 years. But actually, the models tell us much more than that, because when the climate models, which are this red one, are run for more than 100 years, what they get is this red line. They get this red line that is here, okay? So practically, these climate models are telling us that without some volcano, which are these spikes that you see here, without some volcano, climate would have remained more or less constant, not just for 150, 170 years, but it would have remained constant for thousands of years, for more than 1,000 years, okay? So practically, these models predict a flat climate, okay, flat climate. Now, what is the problem here? The problem here is that the data, here I am using the data shown by the IPCC, okay? These are not my own data. This is the picture that the IPCC itself has produced by using a specific record, the page 2K record, which has some problem. But this picture shows us that the data during the Middle Age were clearly warmer than what the climate models are produced, okay? So essentially, these climate models are not able to produce the warming observed during the Middle Age, not even that little warming produced by the page 2K record, which is a little warming, okay? Not even that little warming. The models are not able to produce not even that little warming that these records say. And this is instead the same kind of picture created in one of my papers, was published several years ago. And you see here that the models are here. These are the data are here. The red one are the data are here. And the models give this record here. So you see clearly that the models do not get the medieval warm period in any way. So the philosophical issue is that how can I trust climate models that do not get the warm period of the past? Okay, how can I say that the climate models are able to correctly interpret the warming during the last century if they do not get the warm period of the past? So it is evident that something is missing in the model. They do not have the mechanism for getting the warm period of the past, and therefore they may not have the mechanism, natural mechanism, to get the warm period of the recent warming as well. So regarding the medieval warm period, we have huge evidences that it existed, in particular on the northern Atlantic, where the evidence are extremely strong because probably the temperature was higher than today over the North Atlantic. Okay, perhaps not everywhere in the world, but we have strong evidence of this warming. And these are some data, some reconstruction of the 2,000 years. So we have a warming now, literally ice age, a warming during the medieval period. Then there was this cold period during the Dark Age, and then there is the Roman warm period here. So you see that there is this something interesting, some oscillation. In Europe, you have the summer temperature of Europe is given by this record here, and you see more or less the same pattern with the Roman period that got relatively warm, even perhaps warmer than the summer of the year 2000. So this means that climate is somehow changing, goes up and down, but we do not see in this record a clear evidence of a anomalous warming during the last 150 years. We see actually a cycle. We start to see a kind of cycle, as you see here, almost 1,000-year cycle, okay? If we go back in time, we find out that there was around 7,000 years ago, this very warm period. It is the Holocene optimum, and the climate models don't get this Holocene optimum. So that is the climate models get this red line here. So again, this climate model fail in reproducing natural variability. We have rich evidence that during the Holocene, the climate went up and down. And this is from the Alps, so we see these oscillations in temperature from the Alps. And if you count, you see this is almost a 1,000-year oscillation that is lasting for several millennia, okay? So we have nearly every 1,000 years you get a warm period. And if you go back in time, you get a very long period because we were in the Holocene maximum, okay? And the evidences of this warm period of the past can be found everywhere on the Alps, because, for example, it is possible to find trees below the glaciers. So the glaciers are retreating, and we found trees under the glaciers. So it's clear that there were periods that were warmer than today. So this is how the Susten Pass in Switzerland looks today. This is how the Susten Pass in Switzerland very likely looked during the Roman period. So what is wrong with the models? So why they are not getting the real thing? Very likely there is something missing, of course. And what is missing? So the only thing that is actually having a millennial oscillation, because this is what we have found in the data, the only thing that has a millennial oscillation are the proxy records of the solar activity, okay, like C14, beryllium-10. So these records produce a millennial oscillation. And so what is maybe missing is the sun. And that sun that, according to the climate models, gives zero effect on the climate change, okay? But that is the only thing that could explain these oscillations that we observe. This is another record where climate and solar data are compared. There are many data, many papers that show a very strong correlation between solar records and climate records for thousands of years. So it is not possible to believe that, it is not possible to claim that solar activity has nearly nearly zero effect on climate change because all record from the Holocene is telling us a different story, that the sun is very likely the most important engine, okay, of climate change. But how the models get this wrong, so wrong on this? The reason is that actually the climate models are using some kind of solar forcing that is very, very low. They're using this record that is very, very almost flat, okay? But there are many ways to reconstruct solar activity. And essentially, there are some records that look like this, and the models are using a record that is nearly flat, so they get zero, okay? They get the sun did not give a big effect on climate change because they're using an almost flat solar record. This is another example. So the models are using this pink, this purple curve as forcing, but there are other authors who claim that solar activity changed in this way, no? So much, much more. Therefore, there is a huge discussion about what the sun did in the past. Somebody believes that the sun did not change much, but those records do not get the climate records. Okay? And there are other people who claim that the sun changed a lot, and that may explain better the climate observations. Now, I am not here to explain all discussion. There's a huge debate about what the sun did because it is a huge field that most climate scientists do not know. But it is very important because the key is to understand how the sun changes and how the sun can affect the Earth. Okay, and there is a huge uncertainty there. This is an example. So there are several different solar forcing reconstructions. The IPCC uses this green curve, but there might be other curves like this, for example. When these are compared against the data, we get what? We get some interesting simulation. Now, first of all, before arriving here, I would like to show this. So when we talk about the sun, we need to think that the sun is not just something that is emitting light, okay? The sun has also a strong magnetic field that actually alters the flux of cosmic rays coming from the space. The cosmic rays and other particles that are moving inside the solar system may affect the cloud cover. There were people, several papers, that suggested that there is some kind of strong correlation between solar records and cloud cover. So I think this is a very important theory. The problem is that climate models do not have this effect. So what happens if, now I am almost finished, what happens if I assume that there are two kinds of forcing, okay? The solar light forcing and a additional forcing, for example, due to cosmic ray or something like that. It is possible to prove that by combining these two forcing, the solar effect can vary from this level, that is what the IPCC produces, no? To these values here, This is much, much bigger. Much bigger. So practically, the climate is oversensitive to solar variation because it is not sensitive only to the light, but it may be sensitive to other solar forcing. So we have a huge response of the climate system to the sun due to this additional forcing. And these models, based on this assumption, fits the data much better. These are the models in this assumption. These are the models for the IPCC. Don't get real oscillations. Additionally, we have other oscillations. Now we talk about many oscillations that are observed in the climate system. All of them have an astronomical origin, also from practically 60 years and below. And this is the results, the final result that I got. So practically what we have here, if we put all this information that I told you, we find out that it's possible to do some kind of prediction from the future by assuming the only scenario that it may be realistic, which is the SSP2 scenario. And then we assume these oscillations due to sun, for example, and we get very good fitting. And, but the important thing is that in this way, the prediction gives us a warming which will remain 2 Celsius degree even using the SSP2, which is not a net zero, which means that if we would like to reach the Paris Agreement target of 2 Celsius degree, we do not need the net zero, okay? Because we need to follow the SSP2, and then climate will do what it will do, and these oscillations will help to keep climate will keep climate change as a reasonable way, at a reasonable level, so there will be no huge warming, so there will be no alarm. There will be no alarm, so there is no need of net zero effect. These are the final results. The IPCC get these results where the only way to get the 2 Celsius degrees using the net zero scenario, but these models, empirical models, suggest that it may be possible to reach the same target by using just the SSP2, which is not a net zero scenario. So it is possible to get a very good results also without destroying our economy. Then I arrived to this point of the book, more or less. You see that there is something missing here. So this is very important. So I don't have time to explain this, but this is actually very important because it explains to you the origin of this oscillation, which have, in my opinion, an astronomical origin, okay? So extend the Milankovitch theory to the millennial a secular scale, and so unfortunately I will not be able to explain you this, but on the book you have a final part that will provide this alternative, this new theory that is improving, and will explain all oscillations somehow. And it is important because in climate change it is not enough to say this model does not work. You need to be able to provide an alternative theory, okay? And the alternative theory is to understand climate variability, natural climate variability. So you need to understand what is the origin of the cycles, and this may provide you an answer. Okay, I stop here.